Welcome to This Explainer. I am absolutely thrilled you're joining us today. If you're a focused learner looking to decode the universal language of motion, well, you are exactly in the right place. Today, we're taking a fascinating look at the foundational rules that govern absolutely everything that moves in our universe, from a falling leaf to a speeding train, or even how your phone's GPS relies on these exact kinematic principles to pinpoint your location on a map. There is a structured, logical way to understand what is happening, and more importantly, what's going to happen next. We're going to unpack the core standards of motion analysis, stripping away all the clutter to give you the direct, visual understanding you need. So, it all really begins with a seemingly simple question. How do we accurately analyze a moving object? Think about that for a second. We see stuff move all day, every day. But to truly analyze it, to predict it, to measure it, and to communicate it scientifically, we need a rigorous system. We need a definitive solution that takes the chaotic movement of the real world and translates it into clear, understandable data. This isn't just about watching something move. It's about breaking that movement down into its absolute fundamental truths. Okay, let's dive into this. What we're really talking about here is kinematics. Essentially, kinematics is the science of analyzing the motion of objects using a foundational set of variables and models. It is the pure description of how things move, without worrying at all about the forces that actually cause the motion in the first place. We're just looking at the what and the how of movement. By mastering kinematics, we gain this incredible ability to freeze time, analyze the mechanics of a moving object, and accurately project its future path. Here is our quick roadmap for today's explainer. 1. Foundations of kinematics. 2. The 6 motion variables. 3. Modeling motion, the toolkit. 4. Motion in 1 dimension. And finally, 5. Motion in 2 dimensions. Let's get started. Section 1. Foundations of kinematics. Setting the stage for motion. The core standard we're examining today dictates exactly what we need to focus on. It states we must analyze the motion of objects using time, distance, displacement, speed, velocity, and acceleration. That quote right there is our North Star for this entire explainer. These aren't just random vocabulary words. This is the specific, mandated set of criteria required to fully comprehend physical motion. If you want to analyze an object's journey, you literally cannot do it without addressing these specific concepts. Moving on to Section 2, the 6 motion variables. Think of this as the alphabet of motion. Let's look at our first pair of variables, distance versus displacement. Now, in everyday conversation, we use these words pretty interchangeably, right? But in physics, they are fundamentally different. Distance is the total ground you covered. Imagine wandering around a giant maze. Your distance is literally every single step you took. Displacement, however, is just the straight-line shortcut from your starting point directly to your ending point. It cares only about where you started and where you finished, completely ignoring all that wandering in between. Recognizing this difference is the absolute first step in tracking a moving object accurately. Now, what's really interesting about this is that the same vital distinction applies to how fast an object is moving. Here we have speed versus velocity. Speed is a scalar. It just tells you how fast you're covering distance. Think of the speedometer in a car. It might say 60 miles per hour. But velocity? Velocity requires direction. It's the rate at which your displacement is changing. Velocity is 60 miles per hour due north. This precise scientific distinction is incredibly crucial because changing your direction means you are actually changing your velocity, even if your speed stays exactly the same. To round out our alphabet of 6 crucial variables, we add time and acceleration. Time is basically the canvas on which all motion is painted. Without an interval of time, motion simply cannot exist. We always have to know when and for how long. Acceleration, then, is the rate at which velocity changes. If you speed up to pass a car, slam on the brakes, or even just turn a corner, you're accelerating. Together with distance, displacement, speed, and velocity, time and acceleration give us the complete foundational vocabulary we need to track how objects move. Section 3. Modeling motion, the toolkit. This is the grammar of kinematics. The source material is actually very explicit about how we apply our variables. It commands us to use models, graphs, equations, diagrams to infer motion. We are just making educated guesses here. We are required to use specific, structured tools to deduce and predict movement. Inferring motion means we can look at the data of what has already happened and definitively state what's going to happen next. And that brings us to our ultimate motion analysis toolkit, graphs, equations, and diagrams. Each model serves a distinct, powerful purpose. Graphs let us visually track changes over time, like seeing a velocity curve slope upwards as an object accelerates. Equations provide absolute mathematical exactness, letting us plug in our known variables to calculate the unknown. And diagrams, well, simple drawings with arrows pointing in the direction of velocity and acceleration really help us spatially map out the reality of the situation. You need all three of these in your toolkit to truly analyze motion. Which leads us to Section 4, Motion in One Dimension, Tracking a Straight Line. According to our standard here, we must use our models to infer motion in one dimension. This basically means we take our graphs, our equations, and our diagrams, and we apply them strictly to a single axis. Think of a train moving back and forth on a perfectly straight horizontal track, or maybe an apple dropping straight down from a tree on a vertical axis. It can go forward, it can go backward, but it cannot turn left or right. It's the most distilled, pure form of motion analysis. So the crucial point is understanding the logical flow of solving a one-dimensional problem. It is a two-step process. Step 1, you identify your 6 motion variables along that single straight line. What's the time? What's the velocity? What's the acceleration? Once you've extracted those variables from the scenario, you move to Step 2. You plug those variables right into your models. You draw the diagram of the straight line, you plot the graph, and you solve the equation. By applying our vocabulary and grammar to a single axis, you completely unlock the mystery of 1D motion. Finally, Section 5, Motion in Two Dimensions, Expanding the Reality. Our final standard asks us to confidently infer motion in 2 dimensions. Now, we're no longer just a train on a straight track. We are a car driving on a curving road, or a basketball arcing through the air towards a hoop. We're dealing with an x-axis and a y-axis simultaneously. But here is the amazing secret. We utilize the exact same models. We still use graphs, equations, and diagrams. The framework doesn't change at all. It simply expands to handle the new complexity. And this brilliantly illustrates exactly how that transition works. Whether you're analyzing a simple one-dimensional drop or a complex two-dimensional curve, the foundational tools are identical. The variables, time, speed, velocity, acceleration, they remain exactly the same. The models, graphs, equations, diagrams remain exactly the same. The only thing that changes is the scope, moving from a single axis to multiple axes. You essentially break the two-dimensional motion down into 2 separate one-dimensional problems, analyze them with the tools you already know, and put them back together. It's a beautifully elegant system. We've covered the vocabulary, the toolkit, and how to apply them from a simple straight line to the complex reality of 2 dimensions. You now understand the core foundations of kinematics. So I want to leave you with this final thought to ponder as you look around today. How will you use these 2D models to decode the complex moving world around you? Every car you see passing, every ball you see thrown is perfectly adhering to these exact rules. Thank you so much for joining me for this explainer. Keep observing, keep analyzing, and I'll catch you next time.